4 ramps, 4 balls. Same starting point, same finishing point. One ramp is a straight line, the shortest possible distance between them. One bulges gently, one is a deep, steep plunge, and one is a curve you might not recognize yet. Release them all at the same instant. Watch the straight one. It loses, badly. And the winner is not the steepest either. The winner is that fourth curve, the one that drops hard at the start and then flattens out to run home. Sit with what you just watched. The straight line is the shortest path between those 2 points. It is not the fastest, not by a little. It arrives while the others are still moving. So here is the strange thing. If you want to get from here to there in the least possible time, the answer is not a straight line. It is a very specific curve, not a circle, not a parabola. One exact shape out of infinitely many possible shapes. And now look at where that shape comes from. Take a wheel, mark one point on its rim, roll it along a flat surface, and watch the path that point traces through the air. That is the same curve. Turned upside down, the fastest way down is the track of a rolling wheel. That curve has a name, the Brachistochrone, from the Greek for shortest time. And the question we are going to answer is the one that should be bothering you right now. Why does the longer road win? The answer is that the race is not about distance. It is about speed, and about when you get it. On the straight ramp, the ball accelerates gently and evenly the whole way down. It is slow at the start, and it is still building speed when it crosses the line. On the winning curve, something smarter happens. The curve dives almost vertically at the very beginning. The ball is not traveling toward the target at first. It is falling. And falling is how you buy speed. By the time it levels out, it is already moving fast. And it carries that speed across the long, flat stretch to the finish. So it takes a longer road, and it covers that longer road at a much higher average speed. The extra distance is cheap. The extra speed is worth more. Now here is the part that makes this a real problem rather than a slogan. You might think, fine, then drop straight down and turn right at the bottom. Maximum speed, immediately. Watch that one race too. It loses. Because the corner costs you. All that speed is pointing the wrong way, and you have to spend distance and time redirecting it. So the answer is not as short as possible, and it is not as steep as possible. It is somewhere between the two. There is exactly one shape that trades distance for speed at precisely the right rate, everywhere along its length. Finding it was one of the hardest problems in Europe. June 1696. A Swiss mathematician named Johann Bernoulli publishes a challenge in a journal called Acta Eruditorum and addresses it to the sharpest mathematical minds in the world. The problem is exactly the one you just watched. 2 points, a ball, gravity. Find the path of quickest descent. He already knows the answer. That is the point. This is not a request for help. It is a public test, with a deadline attached, designed to find out who is actually as good as they claim. And it is worth knowing that this was not the first attempt. Nearly 60 years earlier, in 1638, Galileo had looked at the same question in his final book. He worked out that a ball rolling down the arc of a circle beats a ball rolling down any straight line, or any sequence of straight lines. He concluded that the circle must be the answer. He was right that a curve wins. He was wrong about which curve. The circle is fast, but it is not the fastest. And nobody would settle it for another 58 years, because settling it needed mathematics that did not exist in Galileo's lifetime. Bernoulli's deadline came, and was extended into the following spring at Leibniz's request, and then the answers started arriving, 5 of them. One from Leibniz, one from Johann's own brother, Jacob, who he was in a bitter rivalry with, one from L'Hôpital, one from Tschirnhaus, and one with no name on it at all. The unsigned solution came from England. The story that has come down to us is this. Isaac Newton, by then in his 50s and running the Royal Mint, came home from a full day of work at 4 in the afternoon and found Bernoulli's problem waiting for him. He did not sleep. By 4 the next morning he had solved it. Newton was, by this point, thoroughly sick of being drawn into public contests by continental mathematicians, and he sent his answer back without signing it. It did not help. Johann Bernoulli read the anonymous solution and knew immediately who had written it. His remark has outlived almost everything else about the episode. Ex ungue leonem. I recognize the lion by his claw. You cannot hide the way you think. The method gives you away. Now, all 5 men got the same answer. The curve of fastest descent is the cycloid, the path traced by a point on a rolling wheel. Newton's solution is a masterpiece of raw power, but it is not the beautiful one. The beautiful one belongs to the man who set the problem, and it works by refusing to treat this as a physics problem at all. Johann Bernoulli's solution starts with a move that sounds like cheating. He stopped thinking about a rolling ball and started thinking about light. Because light has already solved this problem. Light, traveling between 2 points, takes the path that gets there in the least time. That is not a metaphor. It is a physical principle, and it was known long before Bernoulli. It is why a straw looks bent in a glass of water. Light moves at different speeds in air and in water, so the quickest route between your eye and the bottom of the straw is not a straight line. It is a bent one, and the exact angle of the bend follows a known law. So Bernoulli built an imaginary world. He sliced the space beneath the starting point into thin horizontal layers, and he made light travel faster in each layer than in the one above it, faster and faster as it goes down. Exactly the way a falling ball gets faster and faster as it drops. Then he asked the only question that was left. What path does light take through that stack? Layer by layer, the beam bends, and when you let the layers become infinitely thin, the bent path smooths out into a single curve. It is the cycloid. He had turned a problem about gravity into a problem about optics, and let light find the answer for him. It is one of the most elegant arguments anyone has ever made. You solve the question by finding something in nature that is already solving it. And now the cycloid does something else, which is the detail I find hardest to get over. Take that same curve, shaped like a bowl. Put a ball high up on one side. Put a second ball much lower down. Put a third, almost at the bottom. Release all 3 at the same moment. They arrive together. Not approximately, exactly. It does not matter where on the curve you start. The time to reach the bottom is identical. The ball that starts high has further to travel, but it also gets steeper acceleration, and the 2 effects cancel perfectly. That property has its own name, the Tschirnhaus, the same-time curve, and Christian Huygens had proved that the Tschirnhaus is the cycloid back in 1659, nearly 40 years before Bernoulli's challenge. He was not doing it for fun. He was trying to build a better clock. A normal pendulum only keeps good time if the swing is small. Swing it wider and it takes longer. But a pendulum guided along a cycloid keeps exactly the same period no matter how wide it swings. Huygens built clocks with curved cheeks at the top of the pendulum to force it onto that path. So stop and look at what has happened. Someone asked, what is the fastest way down? Someone else, entirely separately, asked, what curve makes every drop take the same time? 2 completely different questions. The same answer. That is usually a sign that you have found something structural. There is one more reason this problem matters, and it is bigger than the curve. Think about what is actually being asked. Ordinary calculus, the calculus Newton and Leibniz had just built, answers questions like, what is the best number? Where is the highest point on this curve? What value of x makes this quantity largest? The Brachistochrone does not ask for a number. It asks for a shape. Out of every possible curve that could connect these 2 points, infinitely many of them, most of which have no equation at all, find the single one that minimizes the time. That is a question about an infinity of functions rather than an infinity of numbers, and nobody had machinery for it. So the machinery got built. Euler and then Lagrange turned the trick into a general method, and it is called the calculus of variations. And here is where it stops being about ramps, because it turned out that this is how physics is written. Light does not just happen to take the quickest path. You can derive the whole of optics from the assumption that it does. A thrown ball, a planet, an electron. Each one follows the path that minimizes a quantity called the action, not most paths, the one. In general relativity, a planet orbiting a star is not being pulled. It is coasting along the straightest available line through curved spacetime. Again, a shape chosen out of infinitely many by a minimum principle. Johann Bernoulli set a puzzle about a ball on a ramp. The mathematics that came out of answering it is the language physics uses to describe how nature chooses anything at all. So, 4 ramps, and the straight one loses. The shortest path is not the fastest path. The fastest path dives early to buy speed, then spends that speed crossing the distance, and the exact rate at which it makes that trade is fixed by one curve and no other. That curve is drawn by a point on a rolling wheel. It is also the curve on which every ball, dropped from any height, reaches the bottom at the same instant, which is why it ended up inside 17th century clocks. It was posed as a taunt in 1696, solved overnight by an exhausted man who tried to stay anonymous and was recognized anyway by the shape of his thinking. And answering it required inventing a kind of mathematics that now underlies the way we describe light, gravity, and motion itself, all from a question a child could ask. What is the quickest way down? That is the thing about the good problems. They look like toys. You can watch the whole of this one happen in 4 seconds, with 4 balls and 4 ramps, and no equations at all. And then it takes 300 years to finish understanding what you just saw. If seeing why something is true means more to you than being told that it is, subscribe, because that is the only kind of story we tell here. I'll see you in the next dimension.